welcome to my next lecture on network analysis, lecture number 37. So far we have seen that there are three basic elements: resistance, inductance and capacitances. But there will be another not a new element, but there may be coupled coils present in a network, and if coupled coils are there, mutually coupled coils, then apart from self inductances of the coils, another term appears which is called mutual inductance. Today, I will just define very basic things about that and also try to calculate the energy stored in a coupled coils. Recall that if you have a coil, if you have a magnetic circuit like this, suppose it is a magnetic material, and if you have a coil with N1 turns, and if you pass some current through the coil, say a constant value of current, then what happens is this, the current flows like this. In this way, if you draw, it means we are showing correctly the sense of the winding. Now, when current flows through a coil in this fashion, suppose a current flows in a loop like this, then there will be flux produced, the direction of which will be indicated by the thumb. Therefore, here it will be if current flows at any instant of time in this direction, some flux will be created in the core, and this flux is created by this current I 1. This is coil number 1, and it will create a flux phi. Now, this flux will be, this flux is called the total flux created by the coil. So, phi T 1 is the total flux created by coil 1 when it carries I 1 current, when it carries I 1, and number of turns of this coil is N 1, and we know how to calculate phi T 1. This phi T 1 will have two parts. One part phi T 1 we can be written as phi T 1 can be written as phi m 1 plus phi L 1. Okay. So, phi T 1 is the total flux created. It will have two parts. One is called phi m 1 and there will be another part which will not go to the which will be linking the coil alone. It will not flow through the as a mutual flux. So, this one is called mutual flux in the core. So, this total flux is has one component which I have written phi m 1 corresponding to this coil 1, and this is called mutual flux. It will be in the core, mutual flux in the core, and this part is called which will be completing their paths through a part of the core, through the first coil and through the air. It is not in the core, but nonetheless total flux created by the coil number 1 when it carries current I 1 is this one. And what is self inductance? By definition, self inductance of coil 1 will be is defined as flux linkage per unit ampere. So, flux is total flux, that is N 1 phi T 1 total flux linkage when you pass 1 ampere current, that is you divide by 1. This is what is self inductance all about, clear. And this can be also written as N 1 if you put this phi M 1 plus N 1 phi L 1 divided by I 1, and it can be written as two components, that is N 1 phi M 1 by I 1 plus N 1 phi L 1 by I 1. Mind you, this leakage flux will be a little fraction of the total flux created. For example, phi L 1 can be expressed as some say k 1 bar into phi t, a little portion. If the coupling, if all the flux can be 95-98% of the total flux created will be confined to the core, maybe 2%, 3% is leaking. So, K 1 takes care of that. Anyway, so this is the thing. So, self inductance of a coil, of course, to calculate self inductance total flux linkage is to be taken, because that is the definition of inductance of a coil. Sometimes what is called this inductance is called the magnetizing inductance LM1, and this is called the leakage inductance LL1. So, this term is called magnetizing inductance, and this is called leakage inductance. So, total inductance, self inductance of a coil has got two components in general, a component which is contributed by mutual flux, this phi m 1 is mutual flux, and the another component is leakage flux, and this inductance will be pretty small. K 1 is a small number, is small. Small means few percentage of the total flux created, but anyway this is the thing. So, self inductance of the coil is LM1 plus LL1. LM is much larger than LL1, and that also we can write LM1 is much larger than LL1. This is the thing. So, this is this thing. Now, the inductance of a coil. So, henceforth I will not draw the magnetic circuit, I will simply draw this one, and I will say that the inductance of the coil is L1 and it is suppose carrying a current I, which may be time varying. Okay. If it is a time varying current, then we know that there will be induced voltage in the coil L 1 d I 1 dt. We have done so many times. And since inductance is can store energy, sometimes we will represent this also as a source with this polarity of voltage d I 1 dt. And mind you, L 1 consists of those two component of fluxes while calculating L 1. So, this is okay, this is also okay, because inductance or capacitors can store energy, they may be also represented like this without any loss of generality. And depending upon the value of d I 1 dt, sometimes this inductance is going to store energy, sometimes it will pump back energy to the supply, here there is some sources connected and so on. So, anyway, that is the case. So, this is how we represent it. Now, I will draw the same diagram. This part is very important, you now try to understand. This is your magnetic circuit. This is your coil number 1. With N1 turns, and it carries a current of I 1, and suppose there is another coil like this, having N2 turns, and suppose this second coil, this is the second coil. In the second coil, I am not passing any current, no current carrying no current, only first coil carries current. And if first coil carries current, we have seen that it will produce a leakage flux here phi L 1. This one indicates who has produced this flux, coil 1 current I 1 has produced, that is why 1, and there will be flux, mutual flux like this, which is phi m 1. And if it is DC current, there will be no induced voltage here, because this phi L 1 and phi m 1 will have constant value. By applying this rule, right hand rule, it will have a constant value and nothing is going to happen. Okay. Now, mutual inductance between these two coils is defined as mutual inductance. M to 1, that is how I will write. The second one is that coil 1 is carrying current. What is the flux linkage with the second coil, when 1 ampere flows in the first coil. So, for I 1, whatever is the flux linkage, so for 1 ampere, what is the flux linkage per ampere in the second coil. Now, obviously, you can see it is the mutual flux which is going to link the second coil, phi L 1 will only link the first coil. So, I should write it then, flux linkage with the second coil will be N 2 into phi m 1 divided by I 1, that will be the thing, is not M 2 1. Okay. Now, this mutual flux can be calculated. Note that this coil is carrying a current of value. What is the MMF which has produced this one? It is N1 I1, is not? That is what has produced this mutual flux. I am interested in mutual flux grossly to know how much of how much will be the flux linkage per unit ampere. If I pass 1 ampere here, what will be the flux linkage there? So, note that phi m1, how to calculate phi m1? Anyway, I will do it like this. Sorry. Note that H1 produced by first coil, H1 produced by first coil will be N1 I1 divided by L. What is L? L is the length of this flux path, average length L, length of the flux path. We know this H1. How much will be B1, Bm1? It will be mu 0 mu r into N1 I1 by L. L is the flux of the length of the mutual flux path. So, this will be this. What will be phi m1? Phi m1 will be Bm1 multiplied by the cross sectional area of this core. Suppose it is uniformly cross sectional area A. So, it will be Bm1 into A, and let us assume linear magnetic circuit, okay, mu 0 mu are constant. At least to have constant inductance, I must see that it is operating in the linear zone. So, Bm1 into A is the cross sectional area of the core. So, it will then be equal to mu 0 mu r N1 into B m1 into, I am substituting the value of Bm1. So, N1 I1 by L, is not, and into area, This will be the value strength of the mutual flux. Then by definition M21 will be equal to N2, and mind you this quantity N1 I1 is called the MMF, and bring everything down, it will be 1 over mu 0 mu r L by A. I can bring it there. This quantity is called the reluctance, phi m1 by is equal to MMF divided by called this quantity is called reluctance, a constant number. It depends on the core only, core physical dimension and core properties mu 0 mu r. So, A is the cross sectional area. So, this one is nothing but N2 into N2 by I1 was there, and for phi m1 I can write it as N1 I1 by reluctance. R is reluctance of the magnetic circuit, is not. So, M21 will simply become equal to N1 N2 product of number of turns divided by reluctance, that is all, M21. Just note it. Now, the way I have defined mutual inductance, it is in this fashion. In the same way, I could energize only coil 2 and define the self inductance of coil 2 and the mutual inductance caused by coil 2. Let us do that quickly, but effectively. So, in the second case, now excite the second coil alone, excite the second coil alone with some current, say I 2. So, let us draw it quickly. So, this was the thing, this is the core, and there were two coils, one coil was here with N1 turns, but this time I am not going to excite this coil, and the second coil was here with N2 turns, and what I am telling is I am exciting it with some current I 2, some source I have connected, and current will be flowing like this I 2, is not. Now, if current flows like this, then flux will be produced once again, this will produce a flux which will have two components, one is phi m2 and another flux component will be there, which will be leakage flux phi L2. So, when second coil carries current, if phi T1, phi T2 I will say, total flux created by the second coil will be in the same way mutual flux, which is going to link the first coil plus the leakage flux. What these two indicates? Second coil is only carrying current, this will be this thing. Then self inductance of the second coil will be flux linkage with the second coil. When the second coil carries 1 ampere current, that is per unit ampere current, and that per unit ampere current is I 2, I will write it like that, and these two will have then two component N2 phi M2 by I 2 plus N2 phi L2 by I 2, and this total self inductance of the second coil can be written as some magnetizing inductance of the second coil caused by mutual flux plus the leakage flux of the second coil, and LM2 will be much higher than LL2 for a good coupled coil. So, this will be your L2. When you have energized the second coil, flux is produced here and it is only the mutual flux phi M2 which will link the first coil. Then I will say that the mutual inductance of the first coil when second coil carries current, I will write M12 and this will be equal to mutual flux value is phi M2 and it is linking N1 number of turns. So, N1 phi M2 for 1 ampere current in the second coil, that is I 2. That will be the mutual inductance of the second coil when first coil when the second coil carries current. Here I have not assumed any current carried by the first coil. So, this will be the situation. Now, in the same way, what will be here I will write straight away N 1, this let me do also. So, how to calculate phi m 2? You see phi m 2 will be equal to B m 2 into cross sectional area. What is A? A is this cross sectional area of the core. So, B m 2 is how much? It will be equal to mu 0 mu r into H into A. What is H? H is N I by L. This length of the mutual flux path remains same. So, mu 0 mu r. What is the MMF? N 2 I 2 per unit ampere, that is L into A. This will be the thing. So, phi m 2 is this. Put this value of phi m 2 here, N 1 by I 2 was there, into phi m 2 is mu 0 mu r N 2 I 2 by L into A. You see this I 2 goes, and you will be getting N 1 N 2 into mu 0 mu r into A divided by L, which is nothing but N 1 N 2 divided by 1 over mu 0 mu r L by A. And this quantity we have seen, it depends on the physical dimension of the core and the properties of the core, same material. So, this is called, this is the reluctance, this term is reluctance. Reluctance is same for the mutual flux, either you excite this side or that side. Therefore, M 1 2 will be also N 1 N 2 N 1 N 2 divided by reluctance. And in the previous case, when you excited on the first coil, then also mutual inductance M 2 1 was N 1 into N 2 by R. So, here also I will say M 2 1 is N 1 N 2 by R, but this we have seen is same as M 1 2. Therefore, the mutual inductance either you calculate by exciting the primary one coil, first coil, calculate mutual inductance, whatever you will get. If you excite the second coil, then also you will get the same mutual inductance. Got the point? So, M 2 1 is equal to M 1 2. Was there any inconsistency in the suffix of M 1 2? What I told here, this was there, then this is M 2 1 indicating flux linkage there, then second coil carries current. So, M 1 2 second coil carries current M 1 2, and we find that this is equal to M 2 1, has to be. And therefore, instead of writing M 1 to M 2, I now define M by a single variable. So, I say that M is equal to the mutual inductance. Which is same whether you calculate by exciting first coil, see the flux linkage in the second coil, or excite the second coil, calculate the flux linkage in the first coil. Clear? Therefore, from this we will further carry on our discussion of mutually coupled coils. Thank you.